Let's now take a look at an example of using our Laplace transform. So in this case, we're told all of our initial conditions are 0, and we want to use our Laplace transform to solve for y of t. And so if we look at this equation, we notice the similarity between this and the general differential equation we had in the previous video. We notice we have our output, if we call our output y, we have our input over here. Let's say this is our input, our u of t, and then all of these constant valued coefficients are 12, 32, or 32, and our 1 here represent our system. So what we want to do to make this a little easier to solve is transform to frequency, solve it there, then inverse transform back to our time domain to get y of t. As always, I would encourage you guys to pause the video, maybe think about how to set up the problem, give it a go yourself before coming back and watching me solve it. So what we're going to do is we're going to use a couple properties. So we're going to use our linearity property, and we're going to use our differentiation property. And so these come from table 2.2 in the textbook. So our linearity property I'm not going to put here because it's a pretty straightforward one. Our differentiation and time property is a little bit more complicated. So here is our general expression for that. However, in this example, we see the highest derivative that we're going up to is 2. So we have a second derivative, a first derivative. So really we only need to evaluate this expression for n equals 2 would be for that second derivative case, and for n equals 1. And so what we end up having then is for our second derivative, so if we have d squared of f in time, that's going to be the second derivative, which is equal to, so sorry, this is if we're taking the Laplace transform of that, we're going to have s squared times f of s minus s times f of 0 minus f prime. So this k minus 1 here is indicating taking a derivative, so we have f prime of 0, and actually both of these zeros are 0 minus. And so what that means is just on the left side of 0, because sometimes functions aren't continuous at 0. However, in this case we're told assume all initial conditions are 0. And so what that means is that these terms for f and f prime are going to go away, and we'll just have this s squared times f of s. Similar thing if we look at the case of n equals 1, we have the Laplace transform of df, and that's just going to be equal to s times f of s minus f, our time function evaluated at 0 minus, but again, initial conditions are all 0, so that goes away and we get something that looks like this. So combining that with our linearity property, and then the one other thing we need to know is we can use known transform pairs. So if we look at table 2.1 in the textbook, we can say we know what this transforms to. So u of t in time is going to Laplace transform or have a Laplace transform pair of 1 over s in the frequency domain. And again, you could go through and show why that is, but for this class, if you're able to interpret the table and pull that from the table, that's enough. Okay, so putting all these things together, we can now take this equation to our frequency domain. So the second derivative of y is going to become s squared times y of s. And so I'm going to try my best to do here a capital Y to sort of help us distinguish. But remember, all of those initial values were 0, so that's all we have for that first term. Our second term, here, this 12 dy dt, is just going to be s times 12 times s times f of s. But our f is now y, so we have plus 12s capital Y of s. Our next term is just 32y, and so that's just going to become, from our linearity property, 32 times y of s. And then finally, on the other side of the equation, we had 32 times u of t. We said that u of t goes to 1 over s, and that 32 from our linearity property is just along for the ride. So we get something that looks like this. So that's an s in the denominator there. Okay, so now we have our function in the frequency domain. So now we're in our frequency domain. So what we want to do here now is we want to solve for y of s, solve for that y of s, and then once we have that, we can transform back to our time domain. So what we can do over here is we can factor out our y of s on this left side. We notice that every term has y of s. So if we do that, you can see there's an s squared plus 12s plus 32. So let's just go ahead and multiply that over to the other side. So let me keep that on the screen there for a second. So we can have then that y of s is equal to, so we already had a 32 over s, and now we're multiplying that by s squared, the quantity of s squared plus 12s plus 32. So we get something that looks like this. And so looking ahead a little bit, I can write this a little bit differently. I can factor out this term here, and I can say that this is equal to 32 divided by s times s plus 4 times s plus 8. And so of course you could do that with the quadratic equation if you can't see that immediately, or we're going to talk about some ways to do some of this in MATLAB a little bit later on as well. So once we're at this point, we've solved for our y of s. So now what we want to do is we want to transform, so let me write this down here. We want to transform back to our time domain. That is, we want our y of t. And so remember, we had said in our previous video, we're going to do that with something called partial fraction expansion. And so in particular, we're going to look at something called the residue method. There are other methods to do this, but this is the one that I'm going to focus on in the examples and any homework or test we have. Okay, so what it involves doing is basically we want to get this expression in a form such that we can look at table 2.1 and we can say, all right, here are these basic transform pairs. This term looks kind of like this term from the table, so let's use that. And so that's kind of the basic idea. That way we can avoid having to do any sort of difficult calculus with that, with an inverse equation, an inverse Laplace transform equation. So what we want to do first is we want to say we have this y of s, which is equal to, so I'm just going to copy this first, so 32 divided by s times s plus 4 times s plus 8. And so what we're going to do is we're going to say this is equal to some number, which I'm going to call k1 divided by s, plus some other number, k2 divided by s plus 4, plus a third number, k3 divided by s plus 8. And so looking at the right side of this equation, we can do what we talked about earlier. We can compare to the table and we can say, all right, this is pretty easy. So for example, let's just look at this. Even earlier in this problem, we saw that a 32 u of t became a 32 over s. So if we just sort of run that backwards, we know if we have some number over s, then that's going to become that number times u of t in the time domain. And then similar idea as far as what we want to do with those second and third terms as well. But we need to figure out what k1, k2, and k3 are. So let's look at how we find k1. So the idea is we're going to multiply both sides by s. So we're going to multiply this by s, and we're going to multiply everything over here by s. And so what that's going to do is we see our s's are going to cancel out here on the left. Our s is going to cancel out for this k1 term, but we're going to have an s coming and multiplying by the second and third terms. So what we can do is we can then evaluate at s equals 0. And what that does is that causes these second and third terms to go to 0. And what we're left with then is just k1. K1 is the only thing on the right side, so that has to be equal to 32 divided by s plus 4 times s plus 8, evaluated at s equals 0. And so if you plug in s equals 0 here and here, of course we have 4 times 8, which is 32. So we just have that k1 is equal to 1. Similar idea with k2 and k3. So for solving for k2, we're multiplying both sides by s plus 4, and we're going to evaluate at negative 4, the value that makes this this sort of term in the parentheses or circled here equal to 0. So, not showing all the details of that because again, we're just kind of quickly going over this. We would have K2 is equal to 32 divided by S times S plus 8 evaluated at S equals -4. Plugging in -4 for S here and here, we get that K2 is equal to -2. Similar process for K3, we can say K3 is equal to 32 divided by S times S plus 4 evaluated at S equals -8. Plug in -8 for the two locations we have S, and we find that K3 is equal to 1. If you have any questions about any part of that process, definitely let me know and I'll be happy to go into detail. I just don't want to spend too much time in our class time doing that. So what we can say now then is we can plug in those values for K1 through K3. So we have y of S is equal to 1 over S plus a -2 over S plus 4 plus 1 over S plus 8. And so remember, now these terms are simple enough that we can compare to our known transform pairs. So now we do known transform pairs. And we might also have to use some properties. So for example, for our second and third terms, we're going to use our frequency shift property. So here and here. And so this is a common one. Is why I'm not really giving much more explanation as far as why we're using that. This is just one of those things, sort of the more you do these types of problems, the more you get familiar with what types of properties you use when, and you recognize sort of the form in the frequency domain or the time domain that corresponds to that. So using those two tables, table 2.1 and table 2.2 in the textbook, we can then inverse Laplace transform this and say that our y of t is equal to, each term is going to have a u of t, so I'm going to go ahead and factor that out. So we're going to have a 1, and u of t is going to come later. We're going to have a -2 u of t, and then from our frequency shift property, we're going to have an e to the -4t. And then finally, we're going to have plus 1 times u of t. And then from our frequency shift property, e to the -8t. So again, all of that I'm going to multiply by our step function, u of t. And so this would be the answer for our y of t. And so what we can see, if we go back to sort of that general idea that we talked about in the previous video, we now have our output of our system, our input to the system, and then a transfer function which describes our system. And so the beauty of that is that we can say, well, for a given input, we can determine what the output's going to be just by knowing this transfer function. And again, we'll come back and we'll talk about that a little more later. One other thing I want to briefly note, just sort of a terminology thing in the textbook, is a lot of times you'll notice that this u of t is not explicitly written. So this u of t is usually just assumed in the textbook. And so that's because, of course, it doesn't really, we're not concerned about signals that come before we say t equals 0. Sometimes maybe you'll see, instead of writing u of t explicitly, a problem will say for t greater than or equal to 0. So that's something else that you might see throughout the text, but rarely will you see u of t written by the function.